Hello everybody, welcome to another video. For this one we're going to talk about section 6.3, which is partial fraction decomposition. And as usual for these kind of integration techniques, we're going to have to break up the video into two pieces. We're going to talk about the actual algebraic process of the partial fraction decomposition, and then in the next video we're going to go ahead and do some integration along the side with this new technique. Here we go. So polynomials are the easiest type of function to integrate. We know that, and that's part of the reason why we love them. But polynomial is to a integer as a rational polynomial is to a fraction. So it almost feels like rational polynomials should be just as easy to integrate as polynomials. Well, it unfortunately is not. So we have to leverage a big algebraic process or algebraic technique called the partial fraction decomposition, because apparently integration, we can only handle denominators in some sense. So we have to take our big polynomial, rational polynomial that is, and we have to break them into smaller pieces before we can integrate. So let's take a look at this following motivation. If you have 1 over x minus 2 plus 3 over x plus 1, we can easily add them and we get a rational polynomial, 4x minus 5 over x squared minus x minus 2. So of course I'll spare you the details of finding common denominator and combined terms. But we can do that. So if we reverse the process, then the integral of 4x minus 5 over x squared minus x minus 2 dx, so this integral right here, simply equals to the integral of its separate parts. But then integral of sum is the sum integral, so you can break that up. And both of these are a easy u substitution away from being able to easily integrate, right? And both of these are just ln functions, right? ln of x minus 2, and that's 3 ln of x plus 1, and then of course that plus c. So the integration becomes quite easy, but of course we need to be able to reverse engineer that. And this process of taking a complicated rational polynomial into the sum of simpler rational polynomial is called the partial fraction decomposition. And because of how long this word is, or this phrase, I'm going to go ahead and abbreviate it to PFD for the remainder of this section. I will still say it, but on the notes it says PFD. Yeah, that's a lot of letters. Okay, so again, in this first half of the lecture, we're going to focus on the technique. Couple of rules here. So we're going to let p of x over q of x be this rational polynomial. We need to check two conditions. Condition number one is we need to check if q of x can be factored into smaller polynomials. If it cannot be factored, then we cannot apply this partial fraction because there's no partial fraction, right? So you can't break it up any further. Normally, this is not a concern because we have this big juicy theorem that I'm in no way or shape to justify for you, but it basically says the fundamental theorem of algebra, not the fundamental theorem of calculus. Okay, fundamental theorem of algebra turns out it says any polynomial of degrees 3 or higher can be factored into degree 2, which is quadratic, or a degree 1, which is linear function that are irreducible, aka cannot be factored anymore. In some sense, that kind of means in terms of real coefficient polynomial, so no complex numbers involved, the quadratics and linear functions are essentially the building blocks of every possible polynomial. So anything degree 3 or higher can be factored into degree 2 or degree 1s, guaranteed, even though the factor is difficult. Okay, it is guaranteed. So normally that's not an issue, but if you happen to run into a rational polynomial whose denominator is already a linear function or a irreducible polynomial, irreducible quadratic, then you're stuck, right? You cannot use partial fraction decomposition to break up the fraction any further because it's already about broken down as possible. Okay. Case number 2 is you actually have to check if the degree of the top is less than degree of the bottom. Right? We know the degree of a polynomial is simply the number of the highest power of x, right? So if the numerator has a higher power, then we actually have to do long division. So if you do long division and you, for some reason, divides out completely, then the rational polynomial is just equal to an actual polynomial. Then no problem there. Chances are it's not going to divide out cleanly. You're going to have some remainder. And remember that remainder is actually going to be a rational polynomial too. So you just focus on the remainder instead of focusing on the original p of x over q of x. Okay, so basically to apply partial fraction decomposition, you need to check for these two conditions. So let's take a look at the following 3 examples here. Example 1a, f of x equals to x squared plus 5 over 2x squared plus 7. The highest power on top and bottom are actually the same. They're both 2. So in this particular case, you actually have to apply long division. 2x squared plus 7. Normally, you do need to put placeholder. This one, you don't technically need to, but I'm going to put it anyways, just to remind you what placeholders are, right? And then for the divisor, same thing. So, oops, copied them wrong. This is the dividend, so 0x plus 5. And then the divisor is 2x squared plus 0 plus 7. Okay, so the idea here is, you want to match the first term with each other. So I see a 2x squared in the divisor, so I need to multiply by a 1/2, right? So distribute the 1/2. 1/2 times 2x squared is just x squared. 1/2 times 0 is 0x. Oops, that should be a 0x there. Okay, and then of course 1/2 times 7 is 7 over 2. If you want, you can go ahead and write that maybe as three halves. Maybe it's easier to do algebra that way. Even 3.4, even 3.5 is going to be okay here. Preferably fraction if you're dealing with something that's a little bit difficult to work with. But if you know this is a good, easy decimal, then you can definitely use that. But anyways, in this case, I'm going to go ahead and subtract x squared minus x squared. That goes away. 0 minus 0 also goes away. 5 minus 3.5 equals to 1.5. And that's my remainder. But remember, you don't write your remainder just like 1.5, right? That's like, the good old kids, third grade. But here, you actually write that as plus 1.5 over 2x squared plus 7, right? It's 1.5 over the divisor. So after long division, you're going to get 1/2 plus 1.5 over 2x squared plus 7. And now the remainder portion is something that we can potentially apply partial fraction decomposition on. Okay, potentially. In this case, so it also cannot, right? We cannot do that. The reason for that is the 2x squared plus 7, this is not factorable, right? This is not factorable. One way to tell when something is not factorable is to try to solve it and see if we can find a 0, right? Because factor is going to lead you to find a 0 for sure in terms of quadratic. So can this ever equal to 0? Well, it can never equal to 0, right? Because x squared is always positive, or at least 0. So if I multiply by 2, it's the same thing, right? So at least 0. But now if I plus 7 on both sides, then 2x squared plus 7 is at least 7. It's at least 7. Which means it's never going to equal to 0. So by that logic, there could never be a factor of this in the real numbers, of course. Of course, I know that there's complex number factor, but we don't need to worry about that, right? So this one cannot be factored with the real number factors. So therefore, this polynomial is irreducible, which means at this point, this partial fraction, this thing right here, 1.5 over 2x squared plus 7, you cannot perform partial fraction decomposition. Okay. Moving on to the next one, g of x. We got 3x minus 4 over 4x squared plus 6x plus 7. Now this one, degree is no problem, right? Degree at the top is definitely less than degree at the bottom. So that's a check. But we should always double check this quadratic to see if it's factorable. It might not be so obvious to see that this could never equal to 0. But hey, whenever we cannot solve for a quadratic, we can always run into a quadratic formula. I don't need you to go through the whole formula. You just need to know the cases that indicates when this quadratic formula is going to give you what type of answers, right? And to do that, we need to use the discriminant, which is the b squared minus 4ac part. So if you go ahead and plug that in, you get 6 minus 4 times 4 times 7, you get 6 squared, which is equal to 36 minus 4 times 7 is 28 times 4, again, it is 72. Yeah. No. That one. 112. Double check that one. I think I'm right from there. Okay. Either way, the point is this is going to be negative. Now we know that if the discriminant is negative, then the quadratic formula is going to give you two complex numbers, right? Which once again means there's no real value x that's going to give me a 0. That's another way of saying this polynomial, this quadratic, is not factorable. Yeah, it's not factorable. So you cannot apply the partial fraction decomposition in this case. Moving on to part 3. Actually, let me indicate this. So no partial fraction decomposition. And for part A, this part, the circled part, is also no partial fraction decomposition. Okay, so for part C, this one, we can see that the numerator is 1 degree higher than the denominator. So we're going to go ahead and do long division. X cubed plus 6x squared, put a placeholder, and then x squared plus 5x minus 6. Okay, matching the first term, I need to multiply by x. So distribute, I got x cubed plus 5x squared minus 6x. And I'm going to do subtraction. X cubed goes away. 6x squared minus 5x squared is x squared, 1x squared. 0x minus negative 6 is positive 6x. Drag down to negative 7. And now I need to multiply by 1. So 1, and then distribute x squared plus 5x minus 6. And again, I do subtraction here. So I got x squared minus x squared goes away. 6x minus 5x is 1x. 7 minus 6 is negative 1. Right, 7 minus negative 6 is 7 plus negative 7 plus 6. Right, so x minus negative 1. So the remainder is x minus 1. And this remainder obviously is smaller degree than the divisor, which is degree 2. So we know that's a remainder for sure. That means this quotient, right, after long division, this quotient becomes x plus 1 plus x minus 1. x minus 1 all over x squared plus 5x minus 6. Okay, so that's the remainder here. And now if I was to do partial fraction decomposition, I will be using that remainder. So let's write this maybe on the side here. So working with x minus 1 over x squared plus 5x minus 6. And we want to factor this, right? We want to factor the denominator, and the denominator is fairly easy to factor in this case. We got x minus 1 over x, looks like plus 6. Oh, x minus 1. Let's double check. Yeah, this is the right factor. So, I mean, we got 6x minus 1, so the 5x, right? So this is the right factor, but hey, look, we got lucky. We got a cancellation here. So we can go ahead and cancel these two, and we end up having 1 over x plus 6. Now, after the cancellation, this becomes something yet again that's not factorable, right? Because it's a linear function, they're always irreducible. So you can't apply partial fraction decomposition anymore. But on the other hand, you really don't need to anymore, right? This is already about as simplified as you can get, and you can, I mean, this is easily integrable. So in this particular case, this kind of situation does also happen, whereas the divisor could be really big, or in this case, it's a second degree polynomial. So you do have some remainder, but it turns out the remainder cancels out with half or a portion of the divisor. So you have a easier polynomial to work with. But either way, this is you don't need to apply partial fraction decomposition. In this case, is already readily integrable. Okay, so these are some examples that you need to check, in case something goes wrong. It's definitely worth your couple of seconds to double check to make sure that you're working with the right type of setup. Otherwise, you're gonna go through a bunch of algebra, and then you're gonna realize you chose the wrong method to begin with, right? And that's gonna be a huge time waster. Okay, so now that we've seen a bunch of different cases uh, of the stuff that we need to be worried about, now we can get ready to start the partial fraction decomposition process. So if you got a rational polynomial that satisfies these two conditions, then the following process are the partial fraction decomposition process. So step 1, factor q of x into irreducible quadratic and linear functions, right? That's our condition. Condition number 1, we need to be able to factor for us to do partial fraction, right? So that step is inevitable. For each of the factors, step 2 here, for each of the factor from the previous step, set up a fraction using the factor as the denominator. We have 3 rules for that though. Okay, for linear factors, the numerator needs to be one letter. A, B, whatever, one letter. We'll do some example in just a second. For rule number 2, rule B, for quadratic factors, the numerator needs to be of the form letter x plus letter. Okay, in other words, we need a general linear function. So for linear factor on the numerator, we need a general constant function, whereas the quadratic factor, we need a general linear function. Why? Because we always need to have 1 degree lower on top, right? Or at least lower degree. Not exactly 1, but we need the numerator to always have less degree. So for a quadratic, which has 2 degree, at most, the numerator should be a linear function, which is degree 1. Okay? For rule C, if you have a repeated factor, that means if we have something to some power, okay, then we need 1 fraction for every possible power of the factor up to the number of repetition. Okay, Let's see the following example, since will make more sense here. Over here, I got p of x. So this example right here. I got p of x equals to p of x equals to whatever. I don't really care at this point. But over x plus 1 times x squared plus 2 times x minus 3 to the fourth. Okay, so x plus 1 is a linear term. So I'm gonna need a factor for that, a fraction for that. X squared plus 2 is a quadratic. I will also need a factor, a fraction for that. But then I have x minus 3 to the fourth power. So that's a repetition repeated 4 times. So I need 1 for every possible power of it, right, up to the number of repetitions. So I personally like to count down. So I start with x minus 3 to the fourth, and then I do x minus 3 to the third, x minus 3 second, x minus 3 to the first. You don't need to write the first, but it's good to see it complete. So I like to do this countdown thing, but I know some books likes to go counting upwards. Okay, counting down just feels kind of natural, and I know where to end. Basically, naturally, I know where to end. It's up to you whichever you want to do. Okay. Now, rule number A says on top of a linear factor. Well, this is my linear factor. I need one letter. Choose A. For the next one, I have a quadratic. Rule 2 says I need two letters, letter x plus letter. I use A already. I don't want to repeat letters, so this is going to be bx plus c, letter x plus letter. Now the repeat factor, even though they're, some of the earlier ones, right, like this one, that one, right, is higher power, we actually don't look at the repetitions. We don't look at the repetition, we look at the actual factor that's being repeated. In this case, the factor being repeated is just x minus 3, which according to rule A is a linear factor, so I need one letter on the top, right, on the numerator. So D, E, F, G. Okay, I just need one letter each. Even though they're, if you considered the repetition, then the first one is degree 4, second one is degree 3, third degree 2, fourth degree 1, right? If you consider the repetition, but we don't, right? We don't. We just look at what the term that's being repeated. And the term that's being repeated is x minus 3, which is a linear term. So according to rule number 1, one letter. Okay, so all of these is just setting up the letters, setting up the question. And this is typically what I refer to as the setup step. So step number 2 is the setup. Step number 3, as soon as you finish the setup, I'm going to take that entire thing from example 2, from step 2, and multiply by q of x, which is the original denominator. Okay, which is the original denominator. The reason for that is after I multiply by the original denominator, you are going to be left with a polynomial on the left and the right side of that equation, because the original divisor, q of x, is the common denominator, guaranteed, right? So if you multiply an expression by its common denominator, you're going to get rid of all the denominators. Okay? So in step 4, solve for all the letters, right? A, B, C, D, E, F, G in this case, right? There's a lot. We're not gonna do problems like this, but in general, that's what you're doing. There's actually two different ways to do this. I'll show you an example of both of these, and even the mix and match part. But basically, we have two ways. One way is called the Heaviside method, is named after Oliver Heaviside. Okay, kind of a nice little method, often referred to as the shortcut of this type of problem. It depends on the problem. Most of the time, it does work, but sometimes you need a little extra push. But what this means is we're plugging in strategic numbers into a polynomial from the previous steps, and hopefully things is gonna cancel out. That's the dream. Okay, again, I'll show you what that means in just a little bit. Or method number 2 is the quote unquote the universal way, right? So in step 3, you're gonna get 2 polynomials. You're gonna collect like terms, and then you're going to match the degree of the polynomial, the coefficient of each power of x, and then from there you're gonna form a system of equation, and then using the system to solve for all the letters. The issue, as you can probably guess, is like our example here, we got 7 different letters. That means you're going to have a 7 equations, 7 unknown system of equations. And those of you who remember the terror of system of equations, it's going to recognize that is too much work. Okay. Now, we're not going to be dealing with problems like this majority of the times, but there are problems that are still going to end up with a decent sized system of equation. Most of those are going to be pretty easy once you write everything out, but still, it's a lot of extra work. But this is more universal, and there are problems that you cannot do without this method. So again, I'll show you this in just a little bit. After we substitute all the letters, right, after we found out all the value of the letters, and we just go back to the original setup steps, number 2, basically here, right? And I just kind of replace all the variables, all the letters with the number, with their corresponding numerical value, okay? And then I'm done with my partial fraction decomposition. So that's basically it for that step. But after you got the partial fraction decomposition, you have done a lot of algebra work. You might as well double check, right? And the best way to double check is to simply add everything back together. Again, depending on the problem, that could be a little bit of extra work, but ultimately I think it's worth it because you did all these algebra, and there's a decent chance that you might have forgotten a negative somewhere, where you did a silly math, right? 2 times 3 equals to 5 type of deal, and something went wrong. You might as well spend the extra 10-20 seconds add things back together and make sure you got the right partial fraction decomposition. It's just a good habit to have, right? Again, I'm not saying you should always do this. You always have to do this, right? On a test, maybe you run out of time, then you have to go with what you got. But during normal assignments, or if you have some extra time, even on exams, do that, and I think it's worth the time and the effort to double check. Okay. Anyways, there's one kind of small detail here. Look at this note here. Theoretically, you have to remember what the rational root test and the synthetic division. You should go back and maybe revisit those a little bit to help you factor anything that's degree 3 or higher. So if I give you a degree 3 polynomial, you should, in theory, know how to factor it without me giving you the factor. But I'm not going to do that to you all. You should review it for your own sake, I guess. But I know for sure we teach that in Math 111, which is a prerequisite for Math 122 anyways. But because you're here, you should in theory know it. However, it's a technique that is a little bit more tedious than it needs to. So for this particular class, I'm just gonna go ahead and give you the factors. Okay, for anything degree 3 or higher, I will give you the factors. Degree 2, though, you're on your own. You have to be able to check whether it's factorable or it is irreducible. And again, the best way to do that is to try to solve for the zeros or try to use the discriminant of the quadratic formula. Okay? Basically, as the example we were doing earlier. Anyway, so there's, I know I said a lot, but let's go ahead and see some examples here. Example 2. This already looks kind of enormous, kind of a big rational polynomial. But luckily for us, this one turns out to be not too difficult. Let's take a look. One of the first things that you should try is when you see a quadratic, right? You should just try to factor it. Doesn't take that long, or at least it really shouldn't. So here we go. In this case, I'll go ahead and write down this first. So numerator 5x squared plus 12x minus 11 all over x minus 1. This looks like 2x looks like that, right? 2x minus 1 over times x plus 2. So that's -1, that's 4, right? 4 minus 1 is 3. So just double check that real quick. And majority of the times, if things are factorable, then they should be able to be factored fairly easily. If you are stuck there forever, then maybe consider using the discriminant of the quadratic formula. Okay, so this right here is my factor. You know, actually, I'm gonna put this on the side here. I tell you what, just leave it there. So this is my quadratic, my rational polynomial with the denominator completely factored out. Okay, so this is like step 1 here, right? Factor out all the denominator. Step number 2, I'll just write it here. I'll just put a 2 here. We're gonna go ahead and set this up. So 5x squared plus 12x minus 11 over x minus 1, 2x minus 1, x plus 2. Okay, and the setup goes like this, right? I got 3 linear terms, so just simply x minus 1 plus 2x minus 1 plus x plus 2. Okay, and because they're all linear, so on the top I'll just have one letter, so A, B, and C. Okay, so that's step number 2. That's the setup part. Now step number 3 is go ahead and multiply the entire thing by the common denominator, by the original q of x, that is. So I'm going to multiply the whole thing by x minus 1, 2x minus 1, and then x plus 2. Okay, when I distribute, I can kind of see this is really step 3 here. Maybe I'll put step 2 and 3 here. I realize there's a lot of simplification, right? The left side of the equation, the denominators cancels out. I just get 5x squared plus 12x minus 11. But then on the other side, right, when I distribute it to here, the x minus 1 cancel, but the rest remains. So a times 2x minus 1, x plus 2, right? Because only the x minus 1 is canceled. Plus, when I distribute this to b, right, the 2x minus 1 cancel. So I got b x minus 1, x plus 2. Last but not least, when I distribute to the c part, the x plus 2 cancel. I got c x minus 1, 2x minus 1. Okay, so as you can see, I have 2 polynomials on the left side and the right side of my equation, right? So this is what's going to happen in part 3 always, right? If you take a look at step 3 here, multiply the setup by q of x, you're going to get 2 polynomials. And now part 4 is where you start solving the thing. You have 2 options here. One is the heaviside method, and that's the method we're going to use here. But let me talk about 2 real quick, right? The way 2 works is you actually want to multiply all these out, then you got some factor of x squared, some factor of x, some constant terms. You want to rearrange all of them together, write them all out, and then match the coefficient of x squared on the left hand side with the coefficient of x on the right hand side. Coefficient of x squared with coefficient of x squared, right? Coefficient of x on the left hand side matching with coefficient of x on the right hand side. Constant term on the left hand side match the constant term on the right hand side. Okay, that's what method number 2 means. In this method, but in this particular problem, we're going to go ahead and do method number 1, which is the heavyset method, and that is plugging in strategic numbers. What do I mean by strategic? Well, the more I can cancel after plugging that number, in other words, the more zero I will get after plugging that number, the better. And in this particular case, right, I have a lot of multiplications. That means I can potentially create a lot of zeros. So for example, I'm going to go ahead and plug in x equals to 1. The left-hand side, easy polynomial, right? 5 times 1 squared plus 12 times 1 minus 11. That is just 5 plus 12 minus 11, which is 6. On the right-hand side, when I plug in x equals to 1, this term goes away, right? X minus 1 term goes away. So is that, right? Also an x minus 1 term. So if I have a 0 for both of these, then these two expressions goes away. So all I have left is the first expression plugging in 1. So a times 2 times 1 minus 1, 1 plus 2, which is equals to a times 2 times 1 is 2, minus 1 is 1, 1 plus 2 is 3, so a times 3. So I got my first easy equation, right? I got 6 equals to 3a, or a times 3. That means very easily a is equal to 2. Okay, so right away I kind of already got a letter just by plugging in a very strategic number. Okay, so I can actually play this game 3 different times to find all 3 letters. So another one, x equals to negative 2, right? Why do I plug in negative 2? Because I will cancel out with this term and that term, right? Let's erase some of these. Yeah. So this will cancel out with this term and that term. Okay. So plugging in negative 2, I got on the left-hand side 5 times negative 2 squared plus 12 times negative 2 minus 11, which is equal to 20 minus 20. So this is 20, and then this is negative 24 minus 11. It looks like negative 15. Okay, and then, as we were saying, the a term goes away because it's x plus 2. The b term goes away because it's x plus 2. The c term is the only one remaining, so this is equal to c times negative 2 minus 1 times 2 times negative 2 minus 1. Negative 2 minus 1 is negative 3, so negative 3. And 2 times negative 2 is negative 4, minus 1 is negative 5. 3 times 5 is 15, so C is equal to negative 1. Because negative 15 equals to 15C. Just erase that one more time. And here, let me force this down a little bit. And last but not least, let's go ahead and do the very last one. X equals to 1/2. Okay, x equals to 1/2. So on the left hand side, I have 5 times 1/2 squared plus 12 times 1/2 minus 11. So 1/2 squared is 1/4, so I got 5 over 4 here, plus 12 over 2 is 6 minus 11. So I got altogether is that's negative 5 Yeah, so negative, I guess I can, negative 5. Negative 3 and 3/4, right? Double check. I guess we're 17 over 4. That's okay too. Sorry, 15 over 4. Yeah, we're negative here already. So we're negative 15 over 4. That might have to divide later. So writing it um, as this type of fraction is a little bit better, right? Compared to a mixed fraction. Okay. Anyways, plug in the 1/2 is also gonna get rid of A and C. So I have, oh, I also erased that plus earlier. Did that screw me a little bit? No, I think I'm good. Okay, so I got B 1/2 minus 1, 1/2 plus 2. And that's equal to B times negative 1/2, right? 1/2 minus 1. And then 1/2 plus 2 is 5/2. Okay, so multiplying that together is negative 5 over 4b. So if you divide negative 5 over 4 with negative 15 over 4, we got b equals to 3. Okay, so basically I got all 3 of my letters already compared to the I got all 3 letters, which completes my step 4. Okay, my step 4. And last but not least, all I have to do is to replace the original A, B, and C now with the letters that I got, which is 2, 3, negative 1. Okay, 2, 3, negative 1. Actually, for the sake of clearly on your notes, I will just go ahead and write this out. Make it smaller. Just gonna make it a little bit smaller. Okay, and just kind of rewrite the solution here. Already here. So I have 5x squared plus 12x minus 11 over x minus 1, 2x minus 1, x plus 2. This is equal to, a is 2, 2 over x minus 1, plus b is 3, 3 over 2x minus 1, plus c is negative 1 over x plus 2. Okay? And that is the end of my partial fraction decomposition. Again, it definitely should worth your while to kind of multiply this back in, but this right here is the right factor. All right, moving on to the next example. Here we see that the numerator is a relatively big polynomial, 6x cubed plus 2x squared plus 12x plus 9. The denominator is x squared times x squared plus 3. To check the degree, all you have to do is multiply all the highest degree together, right, of each part. So here I have a degree 2. Over here, that's a degree 2. So if I multiply that together, I'm going to get a degree 4. So it is still bigger than that degree 3 on the top. Okay, so this one is still following the rule here. The tricky thing about this particular problem, though, is that that x squared on the denominator is a little deceptive. That's not really a quadratic. Okay, that's not really a quadratic. The way we see it, even if we treat that as a quadratic, we should recognize that is factorable. So we can factor this into x times x, right? So the way we should see this is that x squared is actually x repeated twice. Okay, x repeated twice. So in the setup, we're gonna write 6x cubed plus 2x squared plus 12x plus 9 all over x. I will go as far as write x parentheses, right, inside the parentheses, squared, and then x squared plus 3. Just to remind myself, that is a repeated term. It needs a factor for each one of its powers. So I'm going to have an x squared term, and then an x term, right, where x is the first term, if you will. And then, finally, a x squared plus 3 term. So now I have here, again, it says x squared, but we remember that's x repeated twice. So the factor is still linear. So I just need one letter. Same thing with the second one. This one is a bit more obvious. That's clearly linear. So we put a b, another letter. For the third term, right, we do have a quadratic. So it's going to be cx plus d. Okay, so that's the setup here. Okay, that's the setup here. Now, for this problem, we're gonna apply this. Actually, no, this is not quite yet, not quite to the point of choosing yet, because the next step should be multiplying both sides here by the original denominator. So x squared plus 3. Okay, and then after distribution, I'll have 6x cubed plus 2x squared plus 12x plus 9 equals to a times x squared plus 3 plus b times x times x squared plus 3 plus cx plus d times x squared times x squared. Now this one, we can definitely try the Heaviside method. Okay, so by Heaviside method, we're gonna plug in some numbers. The problem with this is, first of all, you can never really use this kind of term because we're trying to solve for C and D. You don't know what the value is. Okay, to make sure you don't make that mistake. But other than that, the only thing that can give me some zeros, right, some canceling terms, are the x's. In other words, the only thing I can do is maybe do x equals to 0. And then from here, once I plug in 0, right, the left-hand side becomes 9, right, because all these terms with x's goes away, equals to a times the 0 squared plus 3, which is, of course, just 3. And then the bx, x squared plus 3 goes away. Cx plus d times x squared goes away, right? So you just have 3a. And, of course, that's going to tell you that a is equal to 3. So that's all well and good. But I don't have any more, right? Because the x squared plus 3 is not something that I can get a 0 out of, right? Because I cannot plug in complex numbers. So this is all I got. Now, turns out you can actually leverage the Heaviside method throughout this whole problem, and I get the right answer by plugging in random points. It's no longer strategic, basically. You can just plug in numbers. Every time you plug in a number, you're going to get a system equation. You're going to get an equation inside that system equation. And you can actually solve it that way, but at that point it becomes meaningless. You might as well use the traditional method, the method that is guaranteed to work. Okay, so let's go ahead and uh, move this a little bit lower here. Like, why is it so skewed? Oh my god. Let's go ahead and move this a little bit lower here, and hopefully we'll use this later. Why is everything so skewed? Let me go ahead and erase all of this. Just gonna rewrite real quick. Hopefully a little bit better. Anyways, so what are we supposed to do here? Well, unfortunately, you can't get away with this all the time, right? Get away from this all the time. So what we have to do is we have to collect like terms, right? We got to distribute everything on the top, on the right hand side, and collect like terms. So a x squared plus 3a plus bx to the third plus 3bx plus cx to the third plus dx squared. So I distributed everything, okay? And then I like to collect the like terms. So how about the x cubed terms? I got one here, I got one here. Collect them together, I have b plus c x cubed. Collect the square terms together, I got a x squared dx squared plus a plus d x squared. The x term, I just have 3bx, so plus 3b. I like to just put them in parentheses, indicate their coefficients. And lastly, 3a. That's my constant term. Okay? So the left-hand side is still the same. I haven't done anything much. Okay? But now we can see the matching of the coefficients. That's a cube here. 6 is the coefficient for x cubed. Same thing as b plus c. So 6 equals to b plus c. 2 is the coefficient for x squared, and a plus d is the coefficient for x squared. So a plus d equals to 2. 12 is the coefficient for x. 3b is the coefficient for x. 12 equals to 3b. And last but not least, 9 is the constant term, and 3a is the constant term. So 9 equals 3a, but the Heaviside method kind of already gave us that. Okay, you didn't need the Heaviside method. We just got it here first, but it didn't really help that much because once you organize the coefficients together, you get that same result almost immediately. But sometimes it might help. Sometimes it might kind of open up some solutions. Okay, so let me go ahead and just erase this for now, since we got what we needed anyways. So I'll just write it here. So 9 equals to 3a, and from here, maybe I'll write it downwards. Okay, if 9 is equal to 3a, then a is equal to 3. Similarly, 12 equal to 3b, then b is equal to 4. If b is equal to 4 and b plus c equals to 6, then c is equal to 2. Last but not least, if a plus d is equal to 2, but a is 3, then d is negative 1. Okay, so a lot of time, once you have one or two values already solved, then the rest of the system is very easy to solve. right? So at this point, we are ready to write our answers. I'm gonna cheat a little bit by copy and pasting. But when you're writing this, obviously on paper, you don't have this option. Just make sure you copy everything down carefully. Okay, so we got A and B. A is 3, B is 4, and C and D are C and D. C is 2, D is -1. Okay, and that right there is the complete partial fraction decomposition. And of course, you can go ahead and just write that plus -1 into a -1. That's okay too. But it's not the most important step here. Okay, so that is the partial fraction decomposition. This is the example where the heaviside method doesn't really help. You have to use the more standard, more general method to do this kind of problem. Okay. Moving on, finally, to the last example here. Okay. Once again, this is something that does have an extra factor. So for the numerator, x squared plus 3x plus 6. On the bottom, that first term cancels out, or not cancels out, can be factored out. And we get x times x. Oh, actually, I need a little bit more room here. I got x times x minus 1. And then x squared plus x plus 3. Okay? So here, my setup is going to look like x plus x minus 1 plus x squared plus x plus 3. And the first one is a linear term, so one letter. Second is another linear term, so another letter. Third is a quadratic, right? Another letter, 2 letters, cx plus d. Okay, and this one also doesn't really have a it's not factorable. Again, you can quickly do the discriminant, right, of this quadratic. I mean, apply the discriminant, you're gonna have 1 minus 12, which is negative. So yeah, that one is also not factorable. Okay? But it should definitely keep in mind to check. So we multiply both sides by the common denominator. Multiply both sides here by the common denominator. I have room. I think I should be fine. Let's go ahead and find that out. After that, I will have x squared plus 3x plus 6 on the left-hand side. And on the right-hand side, I have a times x minus 1, x squared plus x plus 3 plus b times b times x times x squared plus x plus 3 plus cx plus d times x minus 1. Boy, that's a lot of writing. The good news here is there is at least 2 values that we can plug in that is fairly strategic. And that word is very hard to say for me right now. X is equal to 0. Plug that in. Left-hand side give me 6. The right-hand side, this term goes away, that term goes away. I will just simply have a times 0 minus 1, 0 squared plus 0 plus 3. So that's just equal to negative 1a. No, negative 3a. Yeah, definitely got to be careful here, right? That right there is -1. That right there is 3. Okay. And from here, divide both sides by -3. A is equal to 2. Let's go ahead and do that. Another one that we can plug in, x equals to -1. Actually, just +1. Left-hand side give me 1 plus 3 plus 6, which is equal to 10. And the right-hand side gave me, well, in this case, this one goes away and that one goes away. Okay, so I got b times 1 times 1 squared plus 1 plus 3. And this is equal to 5. So this is equal to 5b. And that means b is also equal to 2. I derped a little bit. Previously, it was just -3. So a equals to -2. Anyway, so in this case, b equals to 2. Yeah, definitely be a little bit careful. A lot of numbers, very easy to make silly little mistakes. Okay, I got b is equal to 2. Now I need to solve for c and d, and this is the kind of the problem. I don't know how to solve for c and d without plugging in a lot of the weird numbers. Yeah, that is kind of difficult. So this is the type of problem where it might be worth your while to kind of mix up the two rules, right? So now I really need a system of equation. I don't need all of it though, because I already have the solution for A and B. I just need things that involve C and D. Okay, that might not be so obvious of what to do here, but if you just kind of think about multiplying the last term, let me write this out. Last term was cx plus d times x minus 1, okay, times x minus 1. This right here, if you kind of imagine forward that out, so distribute the x, I get cx squared plus dx, and then times x minus 1. You don't have to FOIL it, but you got cx to the third minus cx squared plus dx squared and d, so minus d. So I got this this equation here, right? I got this polynomial, which is kind of tedious, I know. But what that does is it tells me that c is involved in x cubed and d is involved in a constant term. So what I have to do is to go through the rest of the other two terms, right? The rest of these two terms, okay? And help myself extract all the constant terms, right? Because, for example, the constant terms help me solve for d. And then I have to extract all the x cubed terms that help me solve for c, right? I know there's a relationship here too with the x squared, but this one's harder to use because I already have a and b here, right? So if whatever equations I got, if they involve a and b, that's easy. I can plug that in. So what I have to do is just to isolate these points that allows me to focus on c and d individually, right? This is why I'm not using the x squared term because that's c and d intermingled together. Okay, so let's find what gave me the constant term. Right, what gave me the constant term? Well, for example, here, this part, this is never gonna give me a constant term, right? Because I'm always gonna multiply a bx. So I don't even need to look at there. What about here? What's gonna possibly give me a constant term? Well, the only one that's gonna happen is when a times, let me highlight this instead, is when a multiplied by -1 multiplied by 3. That's the only way to get a constant term out of that. Right? So what I actually have here is from this equation, right? Again, from this big old equation here, the only constant on the right-hand side is negative 3a minus d. Right? The negative 3a come from here, and the d minus d come from here, right? This d times negative 1, that's the only way you're going to get constant terms. On the left-hand side is 6. Well, what do we know? A is already negative 2. A 3 times negative 2, negative 3 times negative 2 is already 6. 6 minus d equals to 6, which means d is equal to 0. Okay? Now, of course, if you don't believe me, then all you have to do is to multiply out this entire equation, collect like terms, just like how we did it in the previous example. It's just gonna cost you some time, right? Not difficult, but time consuming, right? More tedious. Okay, but this way help you kind of extract that information right away. Now we got d equals 0. Focus on c. Find the x cubed term. Well, this one's a little bit long, right? Naturally. So let me erase something again here. Focus on the x cubed term. Okay, we don't need to worry about the last expression because that's how we extracted the x cubed in the first place. Okay, so we already got what we needed from there. Focus on these two terms, though. Focus on these two terms. Let me underline them instead. Okay, how am I gonna get the x cubed term from this term, from the b term? Well, there's only one way. Bx times x squared. That's the only one that's gonna give me x cubed. For this one, though, for the a terms, for this term, a couple of ways there. Okay, I can do a times x squared. Let me write that down. That's actually equal to a x cubed. Oh, for x cubed. Actually, that's the only way. Oh, we got lucky there then. Yeah, so 3x cubed, that's the only way. And then for the second term is bx cubed plus bx cubed. Now, for the a term, it is definitely possible to have multiple x cubed, multiple way to get x cubed, but in this case, there's none. And last but not least, for the last term, we know we already got the cx cubed. So basically, we have a plus b plus c x cubed on the right-hand side of my equation here, this equation that is. On the left-hand side, there's what? Nothing. There's a invisible 0x cubed, right? Goes to 0x cubed. So you set the coefficients to each other, a plus b plus c equals to 0. And again, we know what a is, we know what b is. We got a equals negative 2, b equals 2, and c plus c equals to 0. The 0 term here. Oh, in this case, c is equal to 0. C is equal to 0 is not right. Where did we make a mistake on? Double check that real quick. AXB. Why is the CX, why is C also equal to 0? I mean, C and D cannot both equal to 0 because that CX plus D term goes away. That's not possible. What happened here? Actually, I have a typo that's unrelated, but let me erase that. There should be a 3 there. That doesn't change much, though. Oh, okay, I made a silly mistake. Okay. Okay, so that's not, so there's actually nothing wrong here. C does equal to 0. My mistake is this part. D here is not a constant term. Dx times -1 is equal to negative dx. Dang. So we actually, the C is the okay part. I don't see any mistakes here, but D, we have to go back and redo this because it's no longer the constant term, it's the x term. Ah, silly. See, guys, it only shows that you know, if you're not careful, a lot of things can mess you up on this part, right? The algebra part, which is why I keep saying it might be worth your while to double check your result at the end. So let's go ahead and redo this, okay? Better to find out here than later, and better me making that mistake than you, right? So serves as a good counterexample, I suppose. Anyways, back to the drawing board real quick. We let me erase this part as well. Okay, so we now find out this negative dx, right? That's gonna be the coefficient of x. So we have to find out all the coefficient of x here. So for this term, the only way to get a coefficient of x is by doing bx times 3. Okay. Similarly, for the a term, let's see, the way to get x is a times x times 3. Let's write that down. So 3ax. But then there's another way to do it. We have a, ooh, not that way. We have a times -1 times x. Maybe I'll highlight it using a different color. A times -1 times x. So minus a x, right? -1 times a times x. For the second one, the b term, right? The only way to get it is 3bx. And last but not least, d is equal to, this last term give me a negative dx. Right? That's why we focus on the x term to begin with. Okay, so now we can combine some like terms. This is equal to 3a minus a gave me 2a, plus 3b minus d x. And we're supposed to match that with the x term on the left, which is 3. Therefore, 3 is equal to 2x plus 3b minus d. And again, we know what a is, we know what b is. So this is equal to 2 times negative 2 plus 3 times 2 minus d. And 3 equals to negative 4 plus 6 minus d. Let's see. Double check that real quick. So I got 3 equals to 2 minus d. I guess d is equal to negative 1. Okay, finally I got all 3 terms here. I believe this is the right answer. So once again, I'll go ahead and cheat and copy and paste here. Copy and paste. Apparently I need a little bit more room. Let me shrink the bottom here. Shrink that a little bit more here. Where's that 5 coming from? Okay, so now this part, I'm just gonna go ahead and erase this part. The final answer here, though, will be I'll put it here. Okay, so a and b, a is equal to negative 2, and b is equal to 2. C is equal to 0, so 0x, and then d is negative 1. D is negative 1. So that right there is the right answer. Okay, and this time I believe this is right. Yeah, this one I believe is correct. So yeah, that's it for this problem. And of course, you should definitely check, right? As you can see earlier, we did fumble a little bit. And it's very likely to make silly mistakes like this, especially with a lot of algebra, a lot of calculation. So, long problem, but I'm glad we still did this. So then you have this example on hand, and hopefully this is going to be helpful for you to do some partial fraction decomposition in this section. Okay, so that's it for this video. Stay tuned for the next half, where we're going to actually talk about how to integrate, how to bring in some calculus into this long algebraic technique. Okay, see you guys in the next video.